Buenos días, muchas gracias por haber venido o estar asistiendo online a este workshop, nuestro primer workshop del Congreso Nanolyme. Mi nombre es Martín Resano, soy el investigador responsable del proyecto y queríamos hoy comenzar presentando el proyecto con 4 charlas de las distintas partes científicas que tenemos que hacer funcionar para obtener los resultados necesarios para el objetivo final, que es el de diagnóstico de la enfermedad de Lyme. Entonces, vamos a empezar con una charla, la primera, de un contenido mucho más médico, que va a dar Raúl Gotzi, del Hospital de la Nemezan. Luego seguiremos con una parte de contenido mucho más bioquímico, que va a dar Melanie Ranseyer, de Diaclon. Y luego nos iremos a la parte más química. Vamos a tener una parte de bioinorgánica que va a dar Joaquín Aluche del CNRS, y finalmente nos iremos a la parte más bioanalítica que va a dar Antonio Bazo de la Universidad de Zaragoza. Antes de eso, Christophe Pechegan nos va a contar un poco la génesis del proyecto, cómo surgió y dónde estamos. Y sin más dilación, Christophe, por favor.
Gracias, Martin. So in a moment, please put the micro.
The micro. Yeah, is.
Thank you, Martin.
Sorry.
I will not speak Spanish. It's better for you. I just wanted to explain you what was the origin of this project, and so I will briefly introduce. Is there something to move from side to the other? So is it working? So I will try to explain the reason why we started to work on this project, on this Nanolyme project. Of course, it doesn't work. So maybe next slide, or maybe if I can press, give me the keyboard, if I can, and I will do it like this. Yes, even like this, it doesn't work. Okay, so just in few words, you know that Lyme disease is due to a bacteria, namely called Borrelia burgdorferi, and this bacteria is contained in ticks, and if there are almost 4% and up to 20% of the ticks which are infected by this bacteria. And normally this bacteria stay in the wild, but sometimes if you are bitten by a tick, you can be contaminated by this Borrelia, and this will in turn might give you the Lyme disease. In Europe, this is about 800,000 people per year. So that's something which is significant. In France, because we have some nice figures from Réseau Sentinelle that report all the cases in France. So you see that it's increasing, but now it seems to be decreasing. It depends. In fact, it depends on many factors like temperature, humidity, and so on, and the proliferation of the ticks in the wild, in the nature. So up to now, we are about 40,000 cases per year. I know that Raouf Gotzi will explain you on a medical point of view what is the Lyme disease, but it's working. So one of the first symptoms is the occurrence of erythema migrans. So that's a good indicator, but this is not systematic, not all the time. But the symptoms could be a neurologic manifestation, antalgia, myalgia, or neurological damages. So now, if we have a look on the bacteria itself, this is a very strange bacteria. This is a snake-shaped bacteria called spirochete, very small, 10 to 20 microns and about 0.3 nanometers. In fact, oops.
This is, yeah. So,
Yes, we are.
enter.
We need to press this one. Yes,
Okay.
sure. There are other pathogens that are not only Borrelia burgdorferi. There are other pathogens which are listed here, and this can cause what is called, and Raouf Godzi will tell you more about that, tick-borne disease. Okay, so this was just the context. Now I'm going, and this is the first time I do that in public, but I'm going to talk about my life, my private life. And this is the origin of this project, in fact, actually. So at this time, my first daughter, Elena, was 10 years old, and she was paralyzed. Suddenly, she became paralyzed by the legs, and I saw her in the bedroom crawling on the floor. What are you doing, Elena? I cannot walk. I need to crawl to move. Well, that's not normal, you know, at 10 years old. But it was just for 5 minutes. After a few hours, okay, it was not a game, you know, it was something serious. So we went to our family doctor, and he was not capable to diagnose anything. Everything looked normal, you know, except that she could not walk. That was the first problem we see. And the situation returned to the normal after a few days. It was something strange. Okay, it seems okay, that's something we cannot understand. And few days or few weeks after, they started again. It was serious. And then the medical doctor told us, okay, you need to go to the medical emergency at the hospital of Po, and you will see if they have another diagnosis, because I cannot do anything else. So we went there, and the pediatric doctor was not even capable to diagnose anything more. Everything looked normal. This is a picture of my place. You know, we are living in this house, and as you can see, we are surrounded by woods, a lot of woods. And I remembered at this time that Elena was bitten by ticks when she was baby. She was about 2 years old, something like that, 2 times. And I suggested to the doctors, okay, this event, that maybe could be, maybe we should have a look on the Lyme disease. They said, okay, why not? We can try. So that's what we did, and we had this very nice results. So you cannot read it because it's too small, but I made a zoom. And what is written there is that they tested some antibodies, IgG and IgM. And in fact, the results, my system doesn't work okay anymore. Anyway, what we can see that is that she was scoring 9 antibody units per milliliter, and for the IgG, and 11 antibody units for the IgM. With that, the doctor said, okay, this is not Lyme disease. There is no occurrence of the Lyme disease, because we consider that patient is affected by the Lyme disease after 10. You know, it was less than 10. We had 9. So the doctors rejected this hypothesis. It was not Lyme. And now we started to be in this situation where the doctor, yeah, it's a good news because you had a very good blood results, and everything is fine. And at this time, Elena recovered the use of the leg. It was, an intermittent situation. And then started what I call a medical errancy, you know, because you are facing a situation where you know that your daughter is sick. There is something which is very bad for her, but the doctors are not capable of doing anything. And some said, you know, it might be in the mind, you know, so maybe we should have a look on that. So maybe she's a bit stressed. Maybe she should relax a bit. How is school and so on? Her school was perfect, you know, she's brilliant. And start exercising, you will feel better. And then I started to say, maybe she should go and see a psychology doctor, and maybe she will feel better, and so on. And we went to the emergency 2 times. And I remember very clearly this time, this doctor, I will not cite the name, of course, but he said, okay, are you sure this is not the Lyme disease? Because, you know, there are some symptoms that are very close to that. And he looked at me straight in the eyes. It read, non, Monsieur Péchéran, ce n'est pas la maladie de Lyme. Okay, it's not a Lyme disease, but very straight, you know. He was in the age of my postdocs, you know, so I was a bit insulted by that this way of talking. And he said, next time, maybe we should consider to have a stay in a psychiatric hospital. And then this was this kind of nightmare, you know, and we were living that for months until one day my wife at the gym, you know, she's practicing sport, and she heard the conversations of some people saying, okay, my son, I think it was a son, was affected by the Lyme disease, and he was cured by a doctor in Lannemezan. Lannemezan, it's a small city, a small city in the Pyrenees, close to Pau, 40 minutes from Pau. So she got the address of this doctor. It was Raouf Gauzy. But Raouf Gauzy, we call him, he was very busy. It was not possible to have a consultation with him. And what he did, he has a network of other doctors with he's working with, and in close collaboration. And we had a consultation with one of these doctors. And then we had another situation, because then this doctor did not reject the hypothesis of the Lyme disease, and they started to set up a treatment. And at the end, Elena was cured after something like 6 months of therapy. And then at this time, we had the suspicion with our last daughter of suspicion of Lyme, because she was already bitten by ticks when she was baby too. And then the nightmare was starting again. And so I said, okay, we need to do something. I am, you know, we need to, this led me to take an interest, I would say, in the tests themselves, you know. And in fact, just a few words on the test. There are 2 kinds of tests. The first test is the direct test, culture, growing the bacteria, or PCR. But as you can see here, they are not very efficient for blood, only 10%, 20%. This is not what is used by the medical doctors. What they prefer is indirect test. This is, in fact, ELISA or the Western blotting. In fact, they consider that when your body is exposed to the bacteria, your body will produce some antibodies to kill the bacteria, you know. And one of the good way, I would say, would be to say, okay, we can detect the antibodies themselves. If there are some antibodies, then you have the Lyme disease. This is what was done for Elena with the test I showed you before. Of course, and unfortunately, I would say, these tests are not perfect. You know, sometimes you can have false negatives, false positives. And also what is even more important is that some people do not develop enough antibodies to be detected. And that's really an issue, because if the bacteria is there and you are not producing some antibodies, you will not be detected. And there are a lot of people which are not detected simply because they are not producing enough bacteria. And so I was thinking that this was not the solution. The indirect diagnosis with antibodies is not the solution. So we should detect the bacteria themselves into the blood, for instance, or the biologic fluids. And so I went back to Raouf Gauzy, and I don't know if you remember this discussion, but I told you, okay, you know, I am an analytical chemist, I'm a research scientist, expert in analytical chemistry and metals and so on. Do you think we can do something? He told me, I don't know right now, but maybe you should meet colleague of mine, Hugues Gascan, and maybe you should invite him in your lab, and maybe you will have a discussion. And I forgot that I had already the idea of detecting the bacteria. I cannot tell you how, because this is there is a patent under process for the moment. But I suggested this idea to Raouf and told me that maybe Hugues Gascan could have an idea. I also go to see my colleague Joachim Alouche in my lab, and they said, okay, that might be a great idea. And you know, that's not so often I have great ideas, you know. So I started to continue on that. And so and so we set up a project, and we tried to make a kind of dream team, and we applied to a national call for project, very selective, very challenging. We call that ANR, and we got this project Nanoscape with this idea of direct detection of the bacteria himself. And so this project was with these partners, IPREM, so my lab, with Joachim Alouche, Antonia Tosca, she's right there, and she was, we had the opportunity to have a PhD with this project, Nangeste as a postdoc, and of course, some doctors, some medical doctors, Hospital of Lannemezan with Raouf Gauzy, Hospital of Angers with Sylvie Chevalier, and Hugues Gascan, which is a great immunologist in Angers and Rennes, and also Diacron. Diacron is a company, it's a French company. It's one of the leaders in the antibody development. And with that, we made this kind of, we run this project. Now the project is at the end, it's finishing in a few months. And so for the moment, we have one published paper. We have 3 peer-reviewed articles to be submitted, but we're limited for the moment because there is a patent which is under drafting. So we cannot submit the paper for the moment. And of course, we had the PhD defense of Antonia Tosca. And this was really the origin. And in the meantime, of course, since we have very great collaboration with, you know, this guy, Martin Resano, Maite, and all the stuff for a long time. And I remember we were in, I think we were in Ljubljana. That you told me, Christophe, maybe we should continue with your idea and maybe try to ask for a POCTEFA project to increase the dimension of the project, you know, and to cross the borders of the Pyrenees. And that's really what we decided to do. And with this, the future of this project is really actually this Nanolyme Interreg POCTEFA project with all these people, and reinforcing, you know, our capabilities in analytical chemistry, also with the Hospital of Miguel Servet and so on, and Lannemezan, of course. And so now we are on the track. We have very promising results. For the moment, we cannot deploy directly this new Lyme test, because you know, this is a long way. But I have the hope that during the frame of this project and during the course of this project, we will end up with something great with all you guys. So I'm speaking too much. Maybe you should stop me sometime.
Muchas gracias, Christophe. Por darnos esta presentación, esta perspectiva personal sobre la enfermedad, sobre el origen del proyecto y sobre cómo se está desarrollando. Sí que vamos un poco con retraso, así que vamos a pasar al siguiente, la siguiente presentación. Aquí. Okay. Raouf Gauzy from Lannemezan Hospital. He's a great experience. Why am I speaking in English? Raúl Gossi from the Nanolyme Hospital. Es un experto en la enfermedad de Lyme y el hospital es un centro de referencia francés en esta enfermedad.
Muchas gracias para la invitación. Yo también voy a hablar en inglés. Alors, en fait, c'est moi qui
¿Puedes pasarlo?
Si,
¿Funciona?
si, fonctionne.
¿Funciona? Ah.
Si. Lyme disease is the first zoonosis in the northern hemisphere, as paludism is the first of the south. The first description in America, in USA, it was in 1975, about after an epidemic in the north of USA. And in the 1982, the microbiologist William Burgdorfer identified the Borrelia in Arctic bight for genus Exodus, Arctic. And in this time, we will see an explosion of the cases, as Christophe said. Actually, in Europe, as you said, there is 100,000 new cases in Europe, and about 100,000 in the USA. This slide is only to say that in 2003 in France, we say the tick exodus was only in the a lot of regions of France, but not in the Mediterranean region, because of the reason of temperature, as you said. But actually, it's very clear that two in Spain and in Mediterranean zone, there is the presence of Exodus and the presence of Borrelia. So there is an evolution with the years. This slide is to make evidence of the cycle of the ticks. So there is three stages. The first stage is larvae. After 1 meal, she comes to the stage of the nymphs, and after another meal at the stage of adults. And you can see that the cycle of the ticks can during above 6 years. There is a notion of the duration of attachment of the ticks to transmit the Borrelia and the bacteria. But there is difference between strains of America and strains of Europa. As you can see in this study of the Pasteur Institute, they identify duration at 8 hours to transmit the disease. So it's very short. You see the spy rocket in the diapo of Christophe. And for the Lyme disease, there is a lot of Borrelia, as you can see, but scientific for the science, actually there is only in the red there is a props of Lyme disease with these strains, but not the others. For example, the genus Borrelia, like Borrelia recurrentis, this bacteria give only recurrent fever, but not Lyme disease. So there is a few, in theory, Borrelia we can transmit Lyme disease. As you said, Christophe, there is an equilibrium between the reservoir of the ticks and the breedadder of the ticks. So, as you can see, rodents are a principal reservoir of ticks, but there is like this parasitoid wasp, whose name is Ixophagus ocaryi, which is destroyed the ticks. And there is also the ants who eat ticks, and there is mushrooms. We can asphyxie the ticks to regulate the populations of the ticks. So the consequence of this all reasons of temperature, of presence of the reservoir, and presence of the predators, and system of regulations of the ticks, there was actually perhaps about 10 years an augmentation of the cases, and we will see in France there is this one is in 2003. That was the incidence of Lyme disease. And in Spain, you can see all the regions of Spain have cases of Borrelia, and it was the incidence and the presence in the tick Ixodes ricinus in this study. Merci beaucoup. Yeah. Good. And it's the same diagram of Christophe, with a stability in France of the incidence actually, and perhaps a little decrease.
No, you can pass here.
Hmm?
You can just,
Okay,
yes,
thanks.
this is the line,
Good.
which is for-
Thanks. So for the presentation, you see there is 3 stages, as Christophe showed us. So the first stage is only in the cutaneous localization, and after, if there is a dissemination, we paste on the second stage, and after about more years, and if there is not antibiotic treatments, we can paste in a late stage. The symptoms and the organs concerned by the Lyme disease, as you can see, there is a cardiac localization in articulation, the muscle also, neurological signs and the localization. And when someone who get treatment as the recommendations proposed, there is, in many cases, persistence of symptoms, as described like this. And they also put in fact, there is a post-infectious disease and not a persistent disease. So for the first stage, erythema migrans, as Christophe said, theoretically, this symptom occurs at the first 30 days. But as you can see, there is an interval more important in certain publications. Another chose. Bon, bref, c'est pas grave. Another thing, voilà, je cherchais en fait. To say it's in the most cases, patients and persons don't see the tick bite. So it's very important because the tick bite can occur in the back, and you don't see the erythema migrans. And the other thing that about 8% of persons with tick bite seen, they don't have erythema migrans, so it's not systematically present. There is the aspect typically of erythema migrans is on target. But as you can see, it's not always the case. It can be full, like this, and sometimes there is a ecchymotic presentation, as in this publication. If there is not antibiotics at this stage, we can pass at the early disseminated stage, or the secondary stage. And in this way, we can have a cutaneous localization whose name is lymphocytima benign skin. As you can see, there is a tumefaction as a cyst, and there is spatial localization, privileged localization, like this in the breast, and the ear, and in the genital organs. So we can have neurological lesions and symptoms with Lyme disease. As you can see, there is a lot of localization and presentation. So there is a facial paralysis, is very current, above all in children. And you can get also deafness and other symptoms. Theoretically, with antibiotics, you can have an amelioration between about 2 months and disappearance of the symptom. This is an study in Spain, and you can see there was 7 patients with this presentation, neurological presentation. And what is interested in this study, there is in 5 patients, there is all anomalies we can attend in a lumbar puncture with anomalies of the cells, but for 2 patients, there was not inflammatory reaction. So sometimes the analyses are not very significant. So the articular lesion is mainly in the knee. It's a typical localization of the articular Lyme disease. But all articulation can be affected. There is cardiac manifestations, as you can see, many cardiac manifestation. Ophthalmic disease, también manifestation and many localization of the Lyme disease. And again, if there is no antibiotics at this stage, we can pass about 6 months or more years in the late disseminated stage. And this stage, the tertiary stage, we can get typically pathognomonic lesion whose name is acrodermatis atrophians. And you can see it is erythema. There is atrophy we don't see very well in these pictures, but it is the aspect of this cutaneous lesion. And in the stage, the late disseminated stage, we can have chronic arthritis, as in your pictures, and neurologic symptoms, chronic neurologic symptom, and también dementia. For the diagnostic, you said, Christophe, it's very difficult, and this slide is from the HAS in February 2000 25. So it's recent, the publication. And you can see, as you said, there is a indirect diagnostic with antibodies, with ELISA, Western blot, with the test of confirmation. But you can see for erythema migrant, normally we don't have to do this serologic test because at this stage is not in about 50 there is a mild probability we can be positive. So we don't have to need to do this test because in many cases it's negative. In this publication, this recommendation of HAS, the thing what was interesting is this one, CXL13. This is a cytokine who can it be in lumbar puncture in the LCS, and when it's positive, it's an argument for neuroborreliosis. And as you can see, it's positive in early Lyme disease and in late Lyme disease. For articulation localization, normally the serology it's positive, but with PCR we can make a diagnostic in the articular liquid, comment on dit? Fluid, or in a synovial biopsy. But as you can see, usually the diagnostic at all the stage, it's with an indirect diagnostic in the most case. There is, in fact, other methods of diagnostic, but the most other tests are not validated actually as ELISpot. It is a cytokine in USA, in Baltimore, there is a few years. They try to see if it will be an indicator of persistent Lyme disease, but it was not. The conclusion was not really good. So ils ont laissé tomber. They forget. Yeah. There is also self-tests, but they're not recommended. And in Germany, regularly we see this test, but it's not validated too. The other tick-borne disease. So in Spain, there is this tick, whose name is Yellowma marginatum, and there is perhaps 2 or 4 cases in Spain of the viruses in the about 2 years, perhaps. And as you can see, the localization and the presence of these ticks in Spain is very important to in the south of the France. These ticks are also in Africa and in Asia. And as you can see, it is a transmission by tick bite. But there is other modes of transmission. The clinic presentation, as you can see, it is digestive symptoms, cutaneous symptoms, and you can have an hemorrhagic phase after, and there is a case fatality rate, as you can see. Can it be important? So it's serious. Another tick, whose name is Rhipicephalus sanguineus, she can transmit different infectious disease agents, as you can see, And the most important is the rickettsiose, ricketsy. There is 3 syndromes who are more are well defined as Mediterranean spotted fever with an scar of inoculation, and after there is a rash, perhaps purpuric features, and with antibiotics, the resolution usually is very good. There is also this syndrome who have 3 names, as you can see, and the particularity is in the scar in the scalp. After this scar, this inoculation with the bacteria of rickettsia, you can have fever, knots in the region of cervical regions, and headache, asthenia, and after alopecia. The last is the LAR with inoculation in the body, all parts of the body, with a local reaction with lymphangitis and satellite lymphadenopathy and flu-like symptoms. Babesiosis in USA is very frequent, but we say in Europe less frequent. Malgré tout, however, there is cases regularly were described in Europe, in France, in Italy, and other as Netherlands. And as you can see, there is above all a tick transmission, but there is cases of transmission. The symptoms, above all, fever, chills, flu-like symptoms, and it's possible to get anemia, jaundice, and it must be very severe in immunocompromised individuals. Another tick is Dermacentor reticulatus, and the bacteria the most transmitted with this tick is tularemia, Francisella tularensis. So it's a bacteria. As you can see, there is a lot of methods of transmissions of this bacteria, not only tick, other methods, but the transmission by the tick is not rare, above all in the United States. The clinic presentation. If there is a contamination, local contamination, we have this form, whose name is ulcer node form, with this ulceration, and there is a node, satellite node in the region. And in this disease, we can have other manifestation like pulmonary infectious and dissemination and septicemia. And if there is septicemia, we can have a cardiac localization or neurologic or in articulation. The tick-borne encephalitis, it's a virus. As you can see, there is 3 subgroups. They are present in the north of the hemisphere, in Asia and in Europe. As you can see, in France, it's limited at the eastern France. And as you can see also, there is another methods of transmission by food, and particularly with the raw milk cheese. What's the clinic of this virus? It's essentially flu-like symptoms and neurological meningitis, encephalitis. There is no treatment. There is a vaccine, but no treatments. So the prevention in Switzerland and in Austria. Ouais. Austria. It's very frequent to do the prevention by the vaccine to avoid this disease. Anaplasmosis, another bacteria. The signs, the clinic signs, is essentially fever, but you can get pneumonia, rash, meningitis, encephalitis. The last one is Bartonellosis, who there is accord, no, ça se dit quoi? Agreement, yeah. A not agreement for pathogenia with the tick. They said there is essentially with the cats, but not with the ticks. There is a controversy with this. But as you can see, this is a study in France in 2016, who show there is 6 patients who get symptoms, chronic symptoms, with presence of Bartonella, and when they get antibiotics, they resolve their symptoms. And all of the 6 patients were bitten by ticks. For the therapeutic aspects, above all, we must do prevention. So there is repellents, natural repellents like citronellidol, and the most important, as Christophe said, in the gardens we can get tick bite. So as the humidity is a reason of presence of ticks, it's very important to have dry areas in the environment to avoid the presence of ticks. The examination after work in the forest and the inspection is very important after exposure. And after a tick bite, we don't need to treat with antibiotics. We can do only a surveillance, and we do to remove the ticks, bien sûr. For the treatment, the treatment is about 10 days, and we can have 4 weeks of treatment, but no more. Selon, comment on dit selon? Depending in the lesion, in the organ lesion. For articular lesion, it's 4 weeks. For erythema migrans, it's 10 days, for example. And for lymphocytoma is 14 days. And for neuroborreliosis, early is 3 weeks, and late is 4 weeks. And if there is, it's the children, there is some molecules were privilegiated for the children. Okay, so it's thing very important, the Jarvis Alzheimer. When you have a treatment, antibiotic treatment, there is sometimes about 20% or more Jarvis Alzheimer reaction whose mechanism is not clear, with reaction, immunological reaction, with liposaccharide is understood. And the manifestation, as you can see, is not specific. And there is an also possibility with tick bites within bacterial transmission. This is the allergy of the antigen alpha-gal. And when you eat red meats, you can develop allergia with digestive symptoms and urticaria. But as you can see, it's not only with meat, with including medication or gelatins, you can see the same. The very problematic that Christophe put in, it's the chronic disease. Lyme can be chronic. So, as I told, actually, the only syndrome who is considered is this one, PTLDS, for post-Lyme disease. And it's a post-infectious disease, not an active disease. And we are not, in the literature, there is a lot of controversy. This is in the recommendation of 2018 for the HS. In this recommendation, they have recognized this syndrome, SPPT, for syndrome post-tick piqûre tick-borne, and with asthenia, pain, disorders, exclusion of all the diagnostic. And in this syndrome, at this time, they authorized to treat more than 1 month with antibiotics. But the very great problem of these patients, there are more symptoms, not necessarily specifics. As you can see, the COVID, there is more similarities. So it's very difficult to precise sometimes if it's post-infectious disease or post-Lyme disease. Active infectious disease is sometimes very difficult. The controversy, it is nourished also because in some studies, when you prolonge antibiotic therapy, there are good outcomes. The problem is its amelioration don't persist in the time. They hydrochute. Go down. In Spain, for example, there is José de la Fuentes en Castilla y Estrada Peña, qui est une vétérinaire, c'est ça? Vétérinaire?
Veterinario, sí,
Vétérinaire aussi.
de la Universidad de
De
Zaragoza.
Zaragoza, sì,
Sí.
voilà. Hay una publicación de 2023, and you can see it is a citizen interrogation about 405 patients. Some patients fulfilled as a questionnaire, and others no. Yeah, and as you can see, all these patients get a diagnostic of Lyme disease, but for the recover of their health status, you can see only 19 have recovered, and the majority not recovered the health. It's very important, and it's very recent in Spain. So there is a problem with the official protocol of antibiotics. Why there is persistence of the symptoms? There is many hypotheses, but the most probably principal hypothesis is this one, round bodies or cystic forms with a persistent bacteria and reactivation of the bacteria. The other possibility is the biofilm organization of Borrelia. And when you give antibiotics, there is no penetration in this biofilm, so there is persistence. And this biofilm and these round bodies you can get in all organs, in neurologic organs, articulation, all organs. So, in conclusion, as you understand, the new recommendation in France of High Authority of Health recognize essentially persistent symptoms, but unfortunately only as post-infectious disease, and then do not recommended the antibiotic prolongation. But the association of the patient should be because most of the patients, as the two daughters of Christophe, with prolonged antibiotics are cured. So there is always a problem with this. Voilà, là j'ai fini.
Merci beaucoup.
Merci.
Raúl,
Merci.
por esta presentación. Agradecemos a Raúl primero haber venido aquí porque sabemos que los médicos están muy ocupados. Tienen que atender a gente, intentar curarles y Raúl está más ocupado que la mayoría. Nos ha dado mucho miedo con esta presentación, ¿no? Todas las cosas que nos pueden dar las garrapatas. A mí me preocupa todo menos la alopecia. Esta ya no.
Sí.
Esta ya no. Pero a lo mejor fue una garrapata. Bueno, vamos a pasar a la parte más bioquímica, el desarrollo de anticuerpos que nos puede servir para detectarlas. Y tenemos esperando online a Melanie. ¿Me das tú? Esto. Sí, tranquilo. Melanie?
Hi, everybody. You can hear me?
Yes.
Okay, great. So today I will present you in English. I think it's better for you. How we developed monoclonal antibodies for Borrelia characterization. So quickly, who is Diaclone? Diaclone is a private company located in Besançon, so in eastern of France. At Besançon site, we have 27 employees, almost half one are dedicated for R&D department. Diaclone, part of Medix Biochemica, has been a major player in the development of monoclonal antibodies and immunoassay for over 35 years. And in 2021, Diaclone joined the group Medix Biochemica. Our experience and expertise coupled to diversity of our products and services make Diaclone a strong partner in characterization and development of antibodies. So, Diaclone offers different types of services, such as antibody development via hybridoma way or phage display. Each technology has its advantages. For example, hybridoma technology, it's more it's more adaptive for smaller budgets, and it's then possible to supply a customer with cell banks of clone of interest around 8 months. Phage display offers more possibility in terms of immunized species. Today, Diaclone is fully capable to immunizing llama, rabbits, and chickens, in addition of mice. It's possible to develop antibodies more quickly for certain projects, but there are some exceptions where the hybridoma is more suitable. It's possible to switch from an hybridoma to a recombinant antibodies. This is often done when hybridomas are not stable, or when we want to improve the yield of clones. And antibodies can be also reformatted or chimerized when the clients want this type of request. We also offer custom antibody and antigen production services. Samples can be provided for clients, and we can perform a characterized by testing in presence from endotoxin or hybridoma in samples. We can also demonstrating the affinity of an antibody for this target. It's very dependent of client requirements. And another Diaclone bestseller products are ELISA and ELISpot kits. We can propose how customer to use of our expertise and knowledge to develop custom ELISA or ELISpot kits according to their needs. And finally, another range of Diaclone services is the cellular assay. For this part, antibodies can be our tools or samples to be characterized. We propose to set up tests to identify possible bioactivity of antibody or antigen. We can demonstrate potential therapeutics use via in vitro test, and develop ADCC or ADCP tests. And of course, we sometimes need to conjugate antibodies to biotin or other fluorochromes or enzymes for our tests. So it's a service we can provide for our customer. As a part of development of anti-Borrelia antibodies, we used the hybridoma techniques, which consist to immunize mice with an antigen, a peptide, or in this case, a bacteria. After immunization protocols, we harvest B cells to fuse them with the mouse myeloma. The screen techniques depend on the aim of the project. Generally, with Diaclone screen, we perform his screening by ELISA or flow cytometry. For nanoscale project, ELISA and flow cytometry were used to identify the best interesting hybridomas. Then small quantities around 2 milligrams, but it depends of client request, are produced for the most interesting candidate, and purified antibody can be evaluated in different characterization tests. to select best candidate for making monoclonal antibodies for the end of the project. So during this project, many steps were optimized for how existing protocols. Borrelia is a very special bacteria that require a great deal of flexibility and adaptability. Different type of buffer were tested for ELISA and flow cytometry because how usually buffer is not really adaptative for this bacteria. About flow cytometry, different type of staining were tested to identify Borrelia, such as flexibility via fixable viability dyes, usually used for eukaryote cells. We have tried cytogreen labeling, but it's not really stable for our tests. FITC conjugation was tested too, but the degree of labeling is very low for the candidate tested. So we choose to perform an indirect staining and we optimize the washing steps, which to avoid losing many bacteria as possible. For sample acquisition, a comparison was done between two different equipments. The major difference between both is the fluidic system. The decontamination protocol and acquisition settings were optimized for this project, which have not been necessary for other antibacterial development projects. And we are currently developing a technique for counting Borrelia using flow cytometry without labeling. For ELISA screening, our protocol had to be adapted to identify the ideal coating to characterize this bacteria and developed antibody pairs to identify Borrelia burgdorferi. After several steps of optimization, we succeed in obtaining a well-defined protocol for the Borrelia characterization. And for this project, all the candidates were validated by flow cytometry and ELISA assay. We use E. coli as a negative strand, and we check the specificity of our anti-Borrelia antibodies. Ideally, we would like to know whether how 5 candidates are specific to Borrelia burgdorferi strain or share some epitope with the other strains of Borrelia. To check this, we are waiting for the other strains to be produced by our supplier. So to sum up, development of anti-Borrelia burgdorferi is a challenging project for Diaclone with a lot of process optimization, but we have 5 candidates available that we transfer to Nanoscape partner for testing. We are also available as technical support for our partner to validate and qualify our antibodies for experiment being developed with our tool. We were asked to qualify the affinity of our antibodies, and for this, we will use a biolayer interference. So it's quite similar to SPR. BLE works by using the interference patterns of light reflect from a biosensor surface. This surface is typically coated with a ligand, so in this case, our antibody, which can interact with its target, so in our case, a bacteria. And when the analyte binds the ligand, it causes a change in optical thickness for the sensor surface, which detects a shift in interference pattern. So this experiment, it's very helpful for us to select the most suitable candidate to choose the best candidate to make monoclonal. But it's a really challenging experiment because we never done this with bacteria. So I think they require a lot of optimization steps, but we can try this soon. You're going to tell me what's happened next. Our aim is to make 2 monoclonal candidates for the characterization of Borrelia burgdorferi. And we aim to do the same with the 2 other strains of Borrelia implicated in Lyme diseases, so Borrelia afzeli and garini, such as Christophe and Ralph mentioned it before. This bacteria strain is very difficult to produce, so making it's difficult to identify a good supplier to provide them. As you saw during this presentation, Diaclone is a complete and strong partner to develop monoclonal antibodies. During this project, we use many of our skills to develop high-quality anti-Borrelia antibodies and provide sensitive tools for characterizing this bacterial strain. And Diaclone wants to stay involved in this project after the end of nanoscale funding, because few monoclonal antibodies anti-Borrelia are available on the market, and having this type of antibody would be a real advantage for us. Diagnosis is an important development area for Diaclone, and the Medix Biochemical Group is a big provider of IVD materials. So it's a really interesting project for us. So thanks to Christophe to invite us to participate of nanoscale projects. Thank you. I think I have a quickly presentation, sorry.
Merci beaucoup. Mélanie, one question from Christophe.
This is not a question, yeah. This is just a comment. Thank you, Melanie, for this nice presentation. I wanted to say that due to the rules of the POCTEFA project, it could not be associated like a normal partner. But there is a huge echo. Okay, so I said that it was not possible to have you as a partner, but you appear in the Nanolyme project as a subcontractant. So that means that I really appreciated your last slide saying that the project is not dead after the end of this national project, because now we have this POCTEFA project, and you will be a subcontractant. You are already a subcontractant of this for the production of these antibodies.
Yes,
so it was just a comment. Thank you.
Merci, Christophe. Again, merci, Melanie, for this nice presentation. We know that we need these antibodies, otherwise we cannot really detect specifically the Borrelia. Merci beaucoup, Melanie. So, ahora vamos a a cambiar un poco de campo, vamos al mundo de la bioinorgánica. Joaquín Alush viene de Po y es un experto en la síntesis de nanopartículas, ¿no?, que pueden ser usadas con aplicaciones biomédicas. Sí. Sí. La presentación no es cargada. Sí, la tengo ahí.
The presentation is on the USB key normally.
Oh, USB key.
USB key and the here. Okay.
A ver, no sé si la cómo se llama. No es ninguna de estas, ¿no? Está bien. Vale.
It's just fit this one.
Sí.
Yeah. You hear me? It's okay.
Sí.
It works. I think.
Sí.
Yeah,
Vamos
okay.
a la presentación.
Yes, it's
Ahora
okay.
vamos a ver. Y le doy a presentar. A ver.
Okay. Okay, so good morning, everyone. So I'm Joachim Alouche, and I will speak about Okay. So to characterize all these materials, so we have we combine several techniques. So typically surface techniques. So I will not go further in the details of these techniques, but we have a topsins that allow the characterization of the surface of the materials at the molecular level, so, at the nanoscale level, because we can characterize the composition of the surface of materials at 1 nanometer scale in depth. And we have molecular information of the surface of the materials. We can use also XPS that gives the elemental composition of the surface of the material, but also the quantification of atoms that we have on the surface of the materials. And we are using also G spectroscopy that gives the composition of the surface of the material, but with a very high resolution, because we can map the elemental distribution of the surface of the material at 10 nanometer scale. So it's very important for us for developing nano materials and so on. So first example I began with such type of materials, which is biohybrid nanoparticles. So this is a core shell particles with a gelatin core. It is a biopolymers and a silica shell that can be. We'll not go further in the detail of the protocol of the synthesis. And so we can obtain such type of particles that can be designed for drug delivery applications, so to use in the cancer treatment, for example. So, and we wanted to understand the effect of size of the particles in terms of structuration of the silica shell around the gelatin core. But apart from this understanding mechanism, so we wanted to see the interaction of these particles with cells. So typically, we wanted to know the cytotoxicity of the particles with fibroblasts, for example. So you have such images. And for example, we identified that the particles are embedded inside the cells by endocytosis. And what you can see is that you have a degradation of the core, of the gelatin core within the cell. So this particle can be applied for drug delivery inside the cell to kill, for example, cancer cells. So this is the first examples. Another examples, so for cancer treatment also. So this is again a core shell structure. So you have we wanted to develop core shell particles for drug delivery for cancer cells also, but with a core metallic core made of gold and silver alloy, and coated with a silica shell with the porous structure. And after, we wanted to functionalize the silica shell by nanovalve, organic nanovalves, in order to close the pore of the shell. The idea behind this development is, okay, wanted to put a drug inside the porosity of the shell, and also this nanovalve can be destroyed by using a photoirradiation of the core. So because the core is very responsive to plasmonic features, so you can activate the core to hit the shell and after destroy the nanovalve to deliver the drug. Okay, this is a main aspect of the functioning of the materials. Another type of materials is more or less the same structure, but here we are using in the shell an hybrid shell made of biopolymers and after silica shell around this biopolymer. So to develop these nanoparticles, we had first to develop the core, so the metallic core. So we wanted to follow all the process of the elaboration. So for example, we start with silver nanostructure, and after we use a redox reaction by adding gold ion with the silver nanoparticles. And by this way, we made a redox reaction, so with the creation of hollow structure within the silver particles. So we have oxidation of the silver and deposition of gold around the silver particles. So depending
laser.
yes, depending on the amount of gold that we had, so we change the structuration of the nanoparticles. So we open an increasing hollow structure within the particles, and we displace the optic properties of the particles. So we wanted to obtain, so by developing this core, we wanted to target this region of the light, typically that is called biological window, because in this region we are close to the near-infrared region in which the tissue men are transparent to light. So you can imagine that if you have these particles with cancer cells, and so if you activate the particles inside the cancer cells, so you cannot destroy the human tissue, but you activate the particles inside the body. So I will not go further in the detail in the characterization of this core, but we use a surface technique to identify the mechanism of formation of the particles and so on. After this step, so we coat silica shell around the gold core to obtain such type of particles with a very porous structure and with tubes that come from the center of the particles. So typically, we wanted to obtain these tubes, and after functionalize these tubes, to close the pore and to put a drug inside. Okay, so we wanted also to characterize the interface inside the particles. So we use a specific protocol of preparation of the samples by using cross polishing. So we cut the particles to go in deeper inside the particles. So you obtain such type of cut. And after we characterize the interface by Auger spectroscopy. So the idea is to choose one single particles, and after target the core or the shell in order to obtain the chemical composition of the core or of the shell, and to identify if we have segregation of elements within one single particle. So we are able to do chemical mapping and to identify the elemental distribution at nanoscale within one single particle. And after that, the third step is to functionalize the particles by using organic nanovalves. So you have such type of nanovalves. So we have a macrocycle, a grafting fragment that is grafted on the silica particles, and this macrocycle enter in assembly with the grafting fragments. So we have characterized such type of the whole step of the elaboration of this functionalization by XPS. And finally, we show that we have an effective functioning of the nanomaterials because we test the material with a photochrome, with a fluorophore inside the porosity. After irradiation in the near-infrared region, so we have a delivery of the fluorophore inside the solution. So we have effectively characterized the well-functioning of the particles. So another example, so this is more or less a similar structure, but here we have an hybrid shell around the gold core. And the hybrid shell is made of a combination of silica, but also with gelatin and polylysine. The idea was to see if we have a change in the structuration of the silica that can depend on the nature of the biopolymers. And what we have done is to show the toxicity of the different kind of particles within model cells. And also we have also measured by CPMS, so the quantity of the particle inside the cells. And we have shown that depending on the biopolymer used, so we have a toxicity higher for gelatin, for example, and lower for polylysine. And also, we have better introduction of the particle inside the cell using polylysine. So this is the first step for understanding how the particles can enter interaction with the cell. So we are working also on different type of materials, nanomaterials. For example, here I show you an example of films, inorganic films. So we are using a specific protocol that allows self-assembly of nanopatterns on the surface. So here you have walls with 25 nanometers. So these particles, these films, these nanopatterning films can be used as sensor, for example, because you can grow particles inside the holes. Here you have an example of iron platinum particles, and typically these particles, these membranes can be used as sensors and nanosensors for different types of organic matter. Another example here of films. So this is interesting work that we have done a few years ago. So the idea is to develop films surface that can be photoresponsive to use for cell culture. So typically, we wanted to have photoresponsive cells that can change hydrophobicity and hydrophilicity in order to remove or not the cell after cell culture. So okay, so and to do this, we combine block copolymers and inorganic nanoparticles. Also, we have the high influence of the interface inside such type of films. And for example, we have used an example here with such type of block copolymers. With this block, you have an acid part, so that can be modified using particles with a functionalized structure. So you have here molecules with alcine here, and you can create a click chemistry between this function and this function, and finally obtain a functionalized surface with gold nanoparticles. But also we use polynipam, that is a thermal responsive polymer. So we have dual functionalization on these films, and typically we characterize all the functionalization of this surface, and finally found that okay, this surface is a thermosensitive surface. So when you eat, you change the hydrophobicity of the surface. So we have characterized such properties. Other examples, for example, here. So the idea is to in this type of research is to understand the interaction between nanoparticles and bacteria and microorganisms. So we wanted to understand the mechanism of interaction between nanoparticles and bacteria, but also how the bacteria can impact the materials. Okay, so we have these two ways that is interesting for us. And for example, we published a first article where we wanted to target cells with gold nanoparticles in order to image such cells and to identify some interfaces at the cells level. So typically we use OG spectroscopy in order to have an elemental distribution at very high resolution in spatial resolution, and also we use tough sims in order to have the molecular information on this bacteria. Another example, so wanted to know how cells, how bacteria can use proteases to degrade the surface of particles. So we use a substrate, so core shell particles with gold core, silica shell, and gelatin. that can be substrate for the protease. The idea is to use gold core in order to follow the particles in all our process. We're using our technique that we have in the lab, and to see if the proteases are able to biodegrade the gelatin, even if the gelatin is coated on the particle. Because it's very important, scarce question, is are the entity, the biologic entity, are able to work if the target is grafted on the particle. So it is a very important question. So I will not go further in the detail, but we showed that, okay, here we have the reference particles without gelatin. So we have a silica that we can see by tough seams. After coating with gelatin, we don't see this fragment by tough seam, but when we have biodegradation with protease, we recover this fragment, this clearance. So we have characterized such biodegradation by these techniques, and other techniques also XPS. Last examples with an example that we have recently with Antonia during this PhD. So the idea is a side project from the Nanoscale project, and the idea is to synthesize iron oxide particles and mix these iron oxide nanoparticles with this molecule. This is a precursor, silica precursor, but with the organic part. So you can polymerize silica here, but also you can polymerize the organic part here. So at the end, we obtain composite nanoparticles. This is a composite nanoparticle, but we are able to control the localization of the iron oxide inside the composite. So typically, we can control if the particles, the iron oxide particles, is on the surface of the composite or inserted inside the composite. So, for example, you can see by space that, okay, we have iron on the surfaces here for these materials, but we don't have the signal here for this second one. Okay, but also it's not so evident to identify this localization by microscopy, by electron microscopy, because you have a 2D observation of the materials, and you have a 3D material, so it is not so evident. So to verify, to characterize the real localization of the nanoparticle inside the composite, so we use EDS, for example, here. So EDS is very sensitive to the bulk. So we observe that, okay, in these particles, we detect iron, but by OG, this is a technique surface that we don't observe here iron signal in this particle, but after cut, we can do a mapping of the cut section of the nanoparticle, of one single nanoparticle, in order to identify that effectively we have iron inside the particle and not outside. And finally, by CPMS, we wanted to know exactly, to characterize exactly the amount of iron inside the composite, depending on the structuration of the nanocomposites. So we obtain such results. Typically, we have obtained a quantification of the embedded iron at the single particle level. So I put this slide just to remember, or to resume all the activities that we have in the lab. So I finish here for this presentation.
Merci beaucoup, Joachim, for this nice presentation on all the possibilities that synthesis of nanomaterials can produce nowadays in biomedical applications. Y ahora vamos a la última presentación de Antonio Bajo. Voy a hacer una presentación más analítica de la Universidad de Zaragoza, de lo que estamos haciendo últimamente. Micro.
Okay, hello everyone. I am Antonio Basso. Just 2 hours ago, I knew that I was going to do this presentation in English before I thought it was going. So, for all of you, as Jim said, I'm going to talk about different ways to single particles and single cell, which is what we're doing right now in the lab. So, as a brief introduction, this is the usual setup of an ICP-MS measurement, where the samples typically a solution that's introduced in the system. So we obtain a signal output, which is a stable signal that fluctuates around an average value. Here, the data acquisition is quite slow in the regions, but if we change the samples to suspensions of nanostructures, those can be nanoparticles, cells, maybe microplastics, and we accelerate the data acquisition to the range of microseconds, the signal output changes. And now it's not these signals, but series of intensity peaks that arise from a fluctuating background that provide information on the mass of those entities. Thank you, Martin, for your help. So, oh, now I can't pass the. I know jokes in English. Yeah, no, I can do the presentation in Spanish, maybe French, a little. Yes. Okay. So what we're going today, it's like a little road. It will go from easier measurements to more complex one. And this is the technique that we will be using for this project in the lab for the measurement of the bacteria that Christoph introduced. So firstly, I will talk about how we can transform these intensity events for nanoparticles to characterize for the diameter. Then we will apply those methods to the analysis of yeast. And finally, instead of analyzing this yeast in suspension, as I previously described, we will talk briefly about the characterization in solid samples directly with the use of a laser. So let's start with the first one. As I said, these intensity events can be correlated to the diameter of the nanoparticles. And depending on what of the event are you using, we can distinguish two kind of methods. First, those based on the intensity when you monitor the area of the events. And among these methodologies, you can either use a proportionally constant called transport efficiency. There are two different methods, particle size and the particle frequency, but there are also methods that don't need to calculate for this constant. Those are the transport efficiency independent, where we distinguish the external calibration and the relative method. But not only the area can be used for this analysis, you can also monitor the transit time, which is the duration of the signals. These are the based on time approaches that are also of interest because they provide a direct information on the diameter of the spheres. So since we have many, many methods, the question here is, which one is the best? And I will try to respond this. And for this purpose, we will look to the accuracy, monitoring 7 gold nanoparticles, which are small, metallic, and barely have any background, and 5 silicon oxide microparticles, which are bigger, non-metallic, and have a very intense background. This will be our model particles. And we will also have a look to the precision, evaluated as the combined uncertainty of all the contributions that were found to affect. So let's start with the transport efficiency dependent. As I said, here you have to calculate this proportionally constant. And depending on the reference standard that you're using, we have the particle size, when the standard is of very well-known size, and what we're monitoring is the sensitivity. And for the particle frequency, we don't really need the of well-known size, but the number concentration in the suspension should be known. In this case, what we will monitor is the number of events registered per unit time. Once we have the transport efficiency calculated, then we simply go to the particle mass equation. And here the advantage is very clear. These are the methods most employed because they only require 1 micron of particle standard. However, they need to monitor ionics solutions that we will discuss later that can negatively impact your results. And this, which is its major advantage, will be also its main drawback. Because the more similar the reference nanoparticle is when compared to the sample, the better the results will be in terms of the error. And the more different they are, the errors can be massive. So if we look to the results achieved for the gold nanoparticles on the top and the silicon oxide nanoparticles on the bottom, we can observe that no significant errors were monitored, which makes sense. These methods are the ones being mostly used, so of course they work. And the uncertainty is quite lower for the particle size when compared to a particle frequency, as it's quite difficult to control the concentration of suspensions. But more interestingly, if we look to the uncertainties for the silicon oxide nanoparticles, let's remember that intense background I mentioned before. While the uncertainty for the particle frequency remains more or less the same, around an 8%, that for the particle size really increased. And that may mean that the particle frequency is much less affected by the background because we don't need to monitor the sensitivity. So we move now to the transport efficiency independent approaches, where we can distinguish the external calibration that can be either linear or polynomial, and the relative method. The external calibration is probably the most easy to understand method. We have nanoparticles of different sizes, we construct a calibration curve, and we just interpolate our sample. So yeah, very simple. We don't require standards as the previous methods, and the uncertainty is also very low. But it has some other issues. First is that it's difficult to have nanoparticle standards well distributed around the curve. That means, especially here, that the bigger nanoparticles may govern the calibration on its own. So it may negatively impact the lower nanoparticles, obtaining significant errors. So in order to improve this, we can calibrate not versus the mass, but versus the diameter. In this case, the calibration is not linear, but a third-degree polynomial function. But as you can observe, the standards will be much better distributed. So we will determine the size directly. The uncertainty will be still low, but we require even more micro-nanoparticle standards for the adjustment. And for the relative method, it was proposed by Moreira Alvarez and co-workers, and it's based on monitoring an ionic standard, a micro-nanoparticle standard, and the sample under progressively lower sensitivity conditions. That way, we can construct a curve like the one shown here by plotting the relative drop in sensitivity for the entities versus that of the ions, and the sensitivity of this curve can be introduced in this equation to obtain the mass. Again, the uncertainty quite low, but the limits of detections are, of course, affected because if we have nanoparticles small that are already difficult to detect, if we continue worsening the conditions of sensitivity, then there's not much we can do. So here are the results. Barely any significant error, and the uncertainties are much lower than in the previous case. So now moving for the based on time method, monitoring the time, as I said, is very interesting because we can correlate it directly with the size of the micronanoparticles. And also it's less affected by the sensitivity fluctuations that the instrument may suffer, and also provides safe information. Of course, it has some limitations. First is the occurrence of split events. When we reduce the dual time, which is preferred for this kind of measurements, the events don't appear like a continuous spike, but like series of split events that are separated by a certain space in time. The second issue is how we determine which are the limits of the event. Because in this case here, we can say, oh, this is the spike, but maybe this is, or maybe this is. It won't suppose a major difference for the area, but it's a massive difference when monitoring the time. So in order to circumvent as much as possible this kind of limitations. We did a statistics study by monitoring many split events, and we observed that over 99% of these events are spaced by less than 30 microseconds. So with this idea, and in collaboration with my colleague and personal friend, Lorien Lopez, which is today here, we developed a dedicated script that works as follows. First, it will identify all the points above a certain threshold. Then, by looking to those 30 microseconds, if 2 points are separated by less than this time, then it will consider that they belong to the same intensity peak. And finally, we can remove those spikes that in reality are not a nanoparticle, but simply background. So with this idea, we optimize the dwell time, because our instrument, the Nexion 5000, allows us to use low dwell times. And we observed that the best results were obtained for a dwell time of 20 microseconds, which was used for the rest of the methodology. And here are the calibration curves that we observed. Here for gold, where the linearity is quite nice. And here for silicon oxide, also super good linearity with any problem, but this point here, you may all have seen. And when in ICP-MS, when doing the analysis of nanoparticles, we have this kind of outliers, we usually assume that what's happening is that the nanoparticle is so big that it's not being fully digested. But we know this is not our case, because in the case of the area, the linearity was good for the linear, was good for the polynomial. So nanoparticles are being fully digested. So what's happening? Then we look to the distribution on the top for the area, on the bottom for the time. And for small nanoparticles, we have a good Gaussian for the area and good Gaussian for the time. But for the big ones, while for the area, we have a good and a clear distribution, the positive tail is quite clear for the time. And this suggests that the bigger nanoparticles, even if they're being digested, they're being digested later on the plasma. So the ion cloud doesn't have enough time to fully expand, leading to abnormally low dwell times, transit times. So here are the results. No significant difference, only that case that I mentioned. And the uncertainty in the case of the gold nanoparticles is comparable to that of the particle size, but in the case of the silicon oxide, it's simply awful. And this, of course, because the impact of the background when monitoring the transit time is massive. So now I will answer the question I made in the beginning. So which one is the best method? I don't know if you have any opinion, but the thing is that the decision is quite difficult because there's not a clear winner, and it depends on which are your needs. If you need high precision, then maybe you can go for the transport efficiency that approaches, but maybe you don't have enough nanoparticle standards, so then go ahead and use the transport efficiency dependent, the classic ones. Or maybe you need some safe information, then in that case you can use the time. It works nice. So we continue with our little road. Next stop is the analysis of cells. All these methods we have discussed for nanoparticles, we will apply for the analysis of yeast cells. Because even if theoretically the idea is very similar to analysis of nanoparticles, we will have entities suspended and we will observe these intensity events. In practice, it's much more complex. And it's much more complex because cells are fragile. Also, they are larger. They are able to transport. It's also more difficult to validate here, do a TM measurement. We just see them, we measure them, and we can check if our results are correct. For the cells, it's not so easy. Also, the analyte contents are much lower when compared to a nanoparticle that is fully made of your analyte. And the analyte is not only present inside of the cell, but also outside, especially if you're using some kind of media of the culture. So in order to circumvent the fragility and larger side, we, instead of using the classic production system where the aerosol moves around the walls through many collisions, we moved to this one, much more linear, and so the transport is maximized. To validate the results, as a sample, we use the Selm1 yeast, which is certified for the total content in selenium. And now we'll have these things. And to fix them, we have to know how are we going to design our experiment to obtain the two kind of information. First, the intracellular with low analyte content, and then the extracellular. So for the extracellular, we just monitor the intensity of the background, and we can construct a calibration curve with ionic standards in which to interpolate the intensity to obtain the extracellular content. So an ionic calibration works fine. But for the intensity of the intercellular spikes, we construct the histogram from here. But then we have all the methods I previously discussed. Evaluated the particle size, which is the most commonly used and requires the monitoring of ionic standards, the external calibration with selenium nanoparticles, and finally, the relative method we previously discussed. With this, we obtain the intracellular selenium content, and if we combine the extracellular and the intracellular, we will obtain the total selenium content. And this total selenium content can be compared to the certified value of the SEM1 yeast. So we will know which of the methods is more adequate to evaluate your cells. So these are the results. We can observe how they are very similar between allowing 5 different measurement sessions between the different methods. But for the particle size, which is the one in red, the variability is much more higher. This is even more evident if we look to the total selenium contents, because we can observe here that even if there are no significant errors, there is a certain trend for this method that requires on the measurement of ions to overestimate the content of your cells. And also the variability is higher when compared to the external calibration or the relative approach. So the conclusion here is more or less like a kid's game. The conclusion we achieve is that maybe what makes more sense is if you want to determine ions, then use ions for your calibration. But if you're going to analyze the internal content, that you're going to analyze entities, then if you can, just go for entities for your calibration. And finally, we move to the laser. And why should we use a laser? What's the difference between working with the laser ablation or directly with the suspension? Well, using the laser has many advantages. First, it's much more direct. We simply put the cells in a microscope slide and we ablate them individually. Since we are ablating them individually, it will be unaffected by double events. And we don't have any size discrimination because all of the cells are transported equally. Also, when we're using a suspension, the cell disease may be problematic, but in this case, it's not, because all the cells will be ablated, that's for sure. So the distributions will be monitored in the end, will be representative of the real distributions of the sample. There are many advantages, but here comes the limitation, as always, and it's calibrating. Calibrating in suspension is easy. It's easy to have liquid calibration standards, but when working with solid samples, it's not so easy. One of the strategies commonly used is the use of gelatin standards, that you can make some films containing different concentrations, either of ionic standards or particle standards. And by ablating a certain area of the gelatin film, we monitor the average intensity. And then if we simply calculate with this equation the mass being ablated in every shot, then we can construct this kind of calibration curves. And this works fairly nice, but again, it has some limitations. First being, we need to know the density of the gelatin. And it's not always very easy to know which is the density, because you have a powder, you will mix it with water, all the structure will change. So it's difficult to know. And also, we need to know very well how much mass is being ablated on every shot. So we need to ensure that all the gelatin, all the thickness is being ablated. And also, we need to know that thickness, because we need to characterize that, and it's not so simple. So in order to improve this, we tried to develop a method that is independent of these two sources of uncertainty and also bias, because if we think that we are ablating a certain mass, but we're ablating much more less, then all the calibration will have a very different slope. And then when we go for the interpolation of our sample, the mistakes can be massive. So here the method we propose is based on the particle mass. Here we use gelatin films very diluted nanoparticles. So most of the time, the laser will be ablated nothing, just the gelatin. But at some point, it will reach to 1 nanoparticle. So we will have intensity spike that will be correlated to the mass of monitoring them. We can construct this kind of histogram, like in the previous works. And instead of using the average intensity, we will monitor the central intensity of this distribution. Of course, since our gelatin is much more diluted than the previous cases, we need to monitor for a bigger area. And this is the main limitation of this application, which is that we need longer times. So looking to the results, we applied these methods to the analysis of HeLa cells, which are a cancer cell line, doped with gold nanoparts. And here we observe that the distributions are quite similar, all of them log normal distributions. And we compared the results with the traditional method, just in suspension. And here's the comparison, where we can observe that in terms of accuracy, the particle mass method we developed is the one offering higher accuracy compared to the reference method. Also, it has higher precision than the previous cases, because determining the mass of a nanoparticle contains much less uncertainty than using the mass of the gelatin. And also the repetitivity, during the 3 measurement sessions that were performed is much better for this method. And the drawback is, of course, the time limit that I previously mentioned. So the conclusions of these 3 works I presented today is that single cell is a very powerful tool for the analysis of single cells. And there are multiple calibration approaches that we can use to obtain the information on their content. But still, there is a lot of room for their improvement. So just to conclude, I would like to acknowledge the funding entities, first the Nanolyme, of course, but also la Diputación General de Aragón, el Ministerio de Ciencia, Innovación y Universidades, and finally, my research group for the support. Thank you very much.
Muchas gracias, Antonio, por esta presentación. Hemos empezado un poco tarde, pero vamos a acabar a tiempo. Como sabemos que la ciencia, uno de los efectos secundarios que tiene es dar mucha sed y hambre. Vamos a acabar aquí la presentación y vamos a pasar a tomar algo en el pasillo. Muchas gracias de nuevo por vuestra asistencia. Hemos intentado mostrar las distintas partes del puzzle que tenemos que ensamblar dentro del proyecto